Alright, guys, welcome back to Starstruck Rambler. And welcome back. And I've been a bit quiet lately over the last few weeks, but I'm back and I hope you guys have been enjoying this quiet time. Now, this is a continuation of the um, star and planetary habitability. Quick recap. In my last video, I talked about which kinds of stars are the most habitable. Now, blue stars like Regulus here are, yeah, they are yeah, as you may know, stars have different lifespans. Some live longer, others shorter. Regulars here will have a very short lifespan, few million years, so they're not very habitable because of their short lives. And then red dwarfs, like Wolf 359 here, um, as I mentioned in my previous video, red dwarfs, yeah, because of the high amount of radiation that they give in the early stages of their lives, they're not that habitable for the planets orbiting them. Yeah, sure, they have a very long lifespan, trillions of years, but like I said before, because of the high amount of radiation that they give off, yeah, not very habitable. So the best, yeah, 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 this is what I was talking about, the massive flares that red dwarfs give off. That's the problem. That's the thing that basically kills planets according to the research that we have right now. It's these giant solar flares that um, red dwarfs give off during the early stages that kill planets. Well, they make any planets around them less habitable by basically blowing off the atmosphere. But, oh my gosh, who's doing that? No man. Ruining my video. But, yeah, sorry about that, guys. I hope you guys haven't heard that. But, yeah. Now, the best type of stars that can be habitable are sun-like stars, like in our solar system. Yeah, currently I have our sun put up as an example. These are the ones that are the most likely to have the best chances for life, Earth-like planets. Now to the planets themselves, um, hold on, sorry. Um, Now the reason why stars like the sun are the most likely to have Earth-like planets around them with life is that first of all, once they reach the stable part of their lives, known as the main sequence, they're actually very stable with very few solar flares, or at least not as frequent as with red dwarfs. It takes a very much shorter time span for stars like the sun to get into their stable age. But once they're in the stable main sequence stage, that's where they're really stable for billions of years. stars like the sun can last up to 10 billion years. So versus maybe 1 or 2 million years where they're relatively unstable. So they're most likely to have planets with life on them. Now to the planets themselves, I'll just quickly put in a star like the sun quickly, as an example. Now for the planets themselves, um, that's a bit more iffy, a bit more difficult because around every around every star there's this zone called the habitable zone. Now this red, basically as you can see, there's this red, green, and blue zone. Um, in the red zone here, let's just place one planet in each zone. Now in the red zone, a planet would and let me just turn on the orbits as well, just to make it a bit easier. Now, as you can see, the red, the planet in the red zone, um, it already has a temperature, a surface temperature of 122 degrees Celsius, and that's without an atmosphere. Um, so as you can see, it's already too hot for liquid water. But if I were to turn on the atmosphere, let's say the same atmospheric pressure as Earth, the temperature immediately goes up to 180 degrees Celsius, which is far too hot for liquid water. Then, the one in the green zone, um, this zone is actually far better for liquid water because in the because it's here the temperature is a bit cooler than in the red zone, but as you can see without an atmosphere, it's the temperature is minus 27 degrees Celsius, as you can see. But if I turn it on, let's say again one atmosphere, and it's 64, basically 64 degrees Celsius, which yeah, it's okay. It's a bit warmer than Earth, but yeah, it's already below the boiling point of water, which would give this planet a very moist, very damp tropical climate. And then to the outermost planet, um, here it's already way cooler at 111 degrees Celsius. Sorry. Now again, one atmosphere, and yeah, as you can see, even with one Earth atmospheric pressure, it's still in the negative degrees, minus 39 degrees Celsius, as you can see here. So depending on where the planet is, it's either going to be too hot or too cold, or if it's in the middle, yeah, just right. Now, astronomers call this green zone the Goldilocks zone because that's where the temperature would be basically just right for liquid water. Um, Now it depends on how dense the atmosphere is, how much greenhouse gases there are in the atmosphere. Um, Yeah, there are quite a few factors that determine the habitability of a planet. For one thing, the mass of a planet. Um, yeah, for one thing, the mass. Um, Now, astronomers have determined the rough mass that a planet should have, minimum, about 1.6 times the mass of the Earth. Now, this planet, which has a mass of 2.97, nearly three times the mass of the Earth, um, yeah, this one's already far, nearly twice the recommended minimum or maximum mass for an Earth-like planet. And yeah, basically what this means is the more massive a rocky planet is, the less Earth-like it is. Now the maximum mass for an Earth-like planet, like I said, 1.6 times the mass of the Earth. This one, nearly three times. So it has will have a very low habitability score or Earth similarity index, which in this case would be 59.1. Earth would be basically 100%. This one is barely 60% that of the Earth. Um, on the other end of the scale, which would be yeah smaller, um, yeah okay this one is slightly above the recommended mass for Earth-like planet at basically close to 1.8 times the mass of the Earth, just zero point 0.2 times the mass of the Earth base recommended mass. So yeah, that one could be more Earth-like if it were in the green zone of the habitable zone. Yeah, but if it's in the cold blue zone, then yeah, it's would be a very cold planet. But on the small end of the scale, um, very small planets, Mars-sized planets, like this one here, which has a mass of about, which has a mass of about 30 moons, 30 times that of the moon. That will have a very, it would have a slightly higher Earth similarity than the inner planet here, but um, yes, it has a slightly higher Earth similarity at 78%, but because of its smaller size, its gravity would be much weaker than that of Earth, so any atmosphere it has would be over time lost to the vacuum of space. Um, yeah, because all stars have a solar wind, and this over time blows away the atmosphere of any planet. Now, much larger planets, like the inner planet here and the outer one here, they can hold on to their atmospheres much better than small ones because of their higher gravity. But small ones like this, because of the weaker gravity, they can lose their atmospheres much quicker than their larger counterparts. Um, and then another thing is the rotation. Now, planets that orbit, okay, here's the thing actually. It's a two-part thing, and they're actually both connected. The one is let me just quickly turn the Sonia off. The one is the magnetic field. Let me just turn that on quickly. Yeah, which is this blue zone around the planet. That's the magnetic field. Now, the magnetic field depends on, for one thing, on currents inside the planet, basically inside the core area of the planet, like with the Earth, with inside the outer core, with the what are they called again? Hang on, just a moment, guys. Yes, convection currents. These convection currents are basically areas where hot material rises up, cools down, sinks again, heats up, rises again, up and down with these convection currents. Um, that's one thing. Another part is with the rotation. Yeah, this one is rotating very, very slowly. Um, so, yeah, even if a planet has convection currents, without a fast enough rotational speed, it's not gonna have a very strong magnetic field. It would be more like, yeah, basically the magnetic field for such a slow spinning planet would be basically non-existent. However, if the planet is rotating faster, let's say 2 days, as you can see now, it's spinning a bit faster. Its magnetic field, of course, would be much stronger because, well, we're not quite 100% sure why it's like this, but from the evidence that we have so far, at least with the Earth and the other planets that have a magnetic field, rota- rotation, at least the rotational speed, has also something to do with the magnetic field. Um, for example, Earth and the gas planets Jupiter, Saturn, Uranus, and Neptune all have magnetic fields. Um, yeah, they have pretty strong magnetic fields because they have um, yeah, because of their rotation. But also they have um, at least with Earth, convection on the inside, well, in the mantle and core. Well, with the Earth mostly in the core area, the outer core. Um, Basically, what I'm trying to say is that with the case of the Earth's rotation combined with convection currents in the Earth's outer core gives us our magnetic field. Mercury, Venus, they don't really have a magnetic field. Mercury has a very weak magnetic field. It's basically just 1% that of Earth's. Venus has no magnetic field, just an exosphere because its day lasts 243 Earth days, while its year is 223. Earth days. So its day is actually longer than its year. So Venus has basically no magnetic field. It has convection currents. It is big enough for that, but because it doesn't have such a high rotational period, it just doesn't have a magnetic field. While Mars has a spotty magnetic field, even though it has pretty decent rotational period, basically the same as ours. Its day is basically the same as long as ours, but because it's smaller, it has basically lost its heat faster, so it has, as far as we can tell, very little convection currents. Its mantle is will cool down much faster than that of the Earth, so it has no a barely perceptible magnetic field, just a, as you would call, fossil magnetic field. So yeah, that's another thing that makes a planet habitable. Um, Another thing, let me just turn this off, would be just like in the case with Earth, plate tectonics, where the crust of a planet is broken into sections that each moves relative to each other. Some parts move away from each other, like in the mid-Atlantic ridge. Almost wanted to say ridge, don't know why, but yeah, that's where new crust is formed. Then we have the plate boundaries, where they collide, like in Japan or the Himalayas. This is where one plate basically subducts or dives beneath another. Like I said, Japan, Himalayas, Sumatra, Aleutian Islands, Mexico, the Andes Mountains. These are areas where one plate dives beneath another. And then we have the third one, where they move sideways against each other, like in the San Andreas. Some of you may have seen the movie San Andreas as well. This is where two plates basically slide past each other at several centimeters per year. Plate tectonics in habitability in planets is also very important because it recycles nutrients, also some rocks as well that get brought back to the surface, like carbonate rocks. These are rocks that are rich in carbon, because of weathering. CO2, actually, because of now some rocks, such as carbonates, they have lot of CO2 um, trapped within them as carbon. And my point is with this is that when these carbonates get to a plate boundary, they get recycled back into the atmosphere as CO2 at volcanoes. Now I'm going to go into more detail with that in another video, but plate tectonics, they basically recycle some of the nutrients in the crust back onto the surface, like I said before, CO2, phosphorus, sulfur, uh, and a lot of other minerals, copper, iron. diamonds, for example, okay, diamonds aren't that important, but okay, for us they are important, yes, but yeah, just an, it's just an example, guys. But yeah, I've been rambling on long enough now, and I might go into more detail in my next video. I'm actually glad to be back again. Um, I hope you guys are glad as well, and I hope you guys enjoyed this video. And oh yeah, a little side note. I came across this series a while back, and it's basically a show from North Korea, a ripoff of Disney's The Lion King. Oh my gosh. I think I'm gonna do a let's watch with that show. It's about 50 episodes, and I think I might do a let's watch with that. Um, though I might need to prepare myself for that because from what I've heard, it's a doozy. A I've I've seen a little bit of it here and there, and just yesterday I watched the first episode of it just to get a feel for this show, and yeah, I actually don't know what to make of that show, but yeah, yeah, so yeah, I think maybe from tomorrow onwards, I'm not 100% sure yet, but I'm gonna, I think I'm gonna I think I'm gonna do a let's watch of, of that show, and yeah, if I do, get yourselves ready, guys, because it is gonna be, from what I've seen, nuts. Literally nuts in every sense of the word. So, yeah. See you guys in the next one. Bye.